Can't be in two places at once.
No. All right, this chapter is on a matrix, and you probably would sit here and go, well, I don't know what a matrix is. Probably when I say the term matrix, the only thing that comes to mind with you is the movie, The Matrix. If you've seen the movie, and somebody asked me whether this really has anything to do with the movie or not, and I'll be honest with you, I'm not a big fan. My husband watches the movie all the time. I can't say that I've ever watched it from beginning to end. So I don't know, okay? So I'm gonna let you guys be the judge of whether this has anything to do with the movie or not. The only thing that I can figure is the movie is a complicated mess, okay? Of basically different things happening at the same time or whatever. A matrix is a arrangement of a group of numbers. So a matrix might look like this. Okay, nothing special about it, it's just a group of numbers. Normally this group of numbers stands for something. Now you're gonna do a little bit of stuff where they make you come up with a matrix, but most of the time they just give you the matrix. Okay, each of these numbers in this matrix is considered an element of the matrix, or it's a member of the matrix. The matrix has dimensions to it, and the matrix is always labeled by a capital letter. Okay, we'll call this matrix A. Notice how the matrix, and this is not a technical term, but this is my term, basically have feet and shoulders. Okay, how it goes in like that? Because if you have something that looks like this, it's totally different. Okay, that's telling you to find the determinant of this matrix. We'll get to that later, but right now we're just talking about a basic matrix. Now this matrix has a certain number of rows and a certain number of columns. Do rows go horizontal or do rows go vertical? When you think of rows? They go horizontal because when you think of columns, you think of in front of a house or in front of the White House that you have those columns, and columns run up and down. So this matrix right here has a dimension of 3 by 4. 3 rows, 4 columns. Okay, now that is very important because when you go to put it in your calculator, you're going to have to know the dimension of the matrix to be able to put it in there. Like I said, I'm not going to let you do the calculator quite yet, but we are going to get there. Your calculator, if you've even looked at it at all and been curious about it, above the x to the negative first power, what does that say? Matrix, okay, it's got some matrix capability to it. Not every calculator does, okay, but your graphing calculator definitely does, and it allows you to do different things with a matrix. Much of what we're going to learn to do by hand. Now, matrices are often used for figuring out word problems, okay? Trying to think whether you've ever done one of those logic problems where, there's 5 houses down a street. One's red, one's blue, one's pink, one's purple. And the person who lives in the pink house has a dog but doesn't live next to the person who lives in the yellow house who has a cat. And you begin to lay out, I don't know, have you guys ever done those things? Okay, and so you try and logically figure out who lives next to who based on what their employment is, or based on their animal, or based on their house color. And it can be arranged in a system called a matrix. That's not what we're going to use a matrix for, but that is one way to use it. You do know there's math that can be done. I mean, this is a math class. So there's math that can be done on a matrix, and the first type of math that we would give, and I really didn't leave myself enough room, is scalar multiplication. Now scalar multiplication is when I'm multiplying one particular number times the whole matrix. Scalar multiplication is really the same as distributive property, okay? Now I'm going to have a matrix over here. I'm going to have to write smaller just because I wrote it in the wrong spot on the board. So what I'm going to do is I'm going to go 4 times 4, which is 16. 4 times 5 is 20. 4 times 2 is 8. 4 times -1 is -4. Then I go on to the next row. Or I could do by columns. It really doesn't matter, whatever order you decide to do it in. 8, 12, 0, and 4. 8, 4, 28, and 16. So that's my answer. That's the resulting matrix, okay? Now this is not matrix A. This would be whatever other matrix I want to assign to it, but remember that one, the original one, is matrix A. When I do scalar multiplication, I just multiply that number times every element in my matrix, okay? We good with that? There's nothing. I'm telling you, when everything's said and done, you're going to find this a really easy chapter, okay? It's kind of a cool chapter, but it's a really easy chapter. All right. For two matrices to be equal to one another, they have to completely match up. Is that a true statement? What do y'all think? I'm getting some yeses, I'm getting some no's. Okay, those of you that say no, why is it not true? Reagan, why is it not true?
They're arranged. They look.
They're arranged different, okay? They are not identical. They must be identical for these two to be equal to each other. So, in other words, the first row, first column has to match first row, first column here. It does. That far I get. First row, second column has to match first row, second column. And it doesn't. Okay? This is a 2 by 3 matrix. This is a 3 by 2 matrix. They don't match. Okay? It would be like saying you and your sibling match because you have the same mom and dad. You don't match your sibling, okay? You'd have to look exactly like your sibling to totally match your sibling, okay? So, in order to match this up, I would have to then turn around and write an exact same matrix. And we go, yeah, those two match. They look exactly alike. They're in the same arrangement. And you go, well, that's kind of a stupid concept. But it has variable applications to it, okay? For instance, you knew it was an algebra, so you knew there had to be variables in here somewhere, right? Okay, I tell you that these two match up. Okay, you look at me and you go, they don't look like it to me, okay? They don't look like they match up. Well, I can turn around and I go, okay, first row, first column. This is simply a 2 by 1 matrix. This is also a 2 by 1 matrix, okay? They're the same dimensions. So I can look at this and I can go, well, 2x has to equal y, okay? This has to equal this. And this, 2x plus 3y equals 12. You with me? Okay? This matches with this. This matches with this. So then I turn around and go, okay, how do I solve for the x and y? How would you do it? Like terms. I could do like terms. I mean, we just did a chapter on this. You just did a test on this. Okay, which is why you had to do the last chapter before this chapter. I think I would do substitution. I think I'm in agreement with Reagan. Now I could, if I wanted to, subtract the y so that I have 2x minus y equals 0 lined up here so I could do elimination. But it's set up really good for substitution because this is my key. I know that y is equal to 2x. So down here, rather than putting y, I put what y is equal to. It's equal to 2x. So I've got 2x plus 6x equals 12, so that's going to give me an 8x equals 12. When I divide it, I'm going to get x is equal to 12 over 8, which when I reduce it down, that's going to give me 3 over 2. Okay, so there's my x value. How am I going to find my y value?
Plug that x back in.
Plug it back in right there. So therefore, I'm going to know that y is equal to 3. So this is a 3 over 2, 3 answer. Does that make sense? Okay. Let me give you one to try. Okay, just scrap paper. It's going to come out whole. It's not going to come out as a fraction. All right, solve for x and solve for y. Once you finish that one, I'm going to give you another one up here that's going to be a little bit more of a challenge, but you're going to do it the same way. This one also comes out whole. Once you finish the first one, and let me know when you finish the first one so I can come check it, and then you go on to the second one. You done? Perfect. Okay, do the second one. Perfect. Do the second one. I agree with that one. Hold on 1 second. Oh, it's a negative 8. Because that's negative 56, so therefore it'd be different when you plugged it in there. Did you get it, Vivi? Working on it.
Yeah.
Okay.
So,
All right, I agree with that. Okay. This one is x minus 3y equals 31. Now, elimination. If I multiply that by 2, negative 2. Okay, can you go from there?
substitution, I was like,
I think that would, I mean, you could have done substitution, but I think that would be the hard way to do it.
Okay.
Did you get the second one?
First one.
Do I? Oh, you got the first one now. Okay. Yeah, that's right now.
I have a calculator. I forgot mine, so I'm trying to do it all in my head.
Don't do that. Got the second one? No, it should come out whole. Okay. Make sure that I wrote it right too. Okay. Brought the X over. Brought the Y over. That should be, that's a negative 3y. Because you have a negative 2 and then bring it over, that's a negative 3. Did you get it?
Oh,
You found it?
yeah, you made it.
Did you want
Yeah.
to do the same thing Reagan did? Yep, perfect. Got it. Okay,
No, see,
let me make sure that you wrote it right. Looks right. Okay, so you brought the x over, that's 2x. You brought the y over.
you did it on the other side.
Oh, you did it over here. Okay, so because you had a negative 3y here, this one you multiplied by 3, right? What's 7 divided by 7?
1.
1. Normally. Yeah, perfect. It's funny how easy it is to make careless mistakes in that. Are you getting it?
Chocolate.
Okay.
Going somewhere.
Okay, what I would have done first is I would have put my x's and y's together. So in other words, I would have brought this x over here, so
Yeah.
then I have 2x plus y equals 3. I would have brought that y over, so I have x minus 3y
Yeah.
equals negative 2. Then I would have
Okay.
gone from there. Probably would have
Okay.
multiplied that by 3
Yeah.
so that the y's match up. Okay, so then I have 7x is equal to, that's a negative, right? And then plug it back in.
Yeah.
Okay,
Okay.
you're just making, it can be
Yeah.
done the way that you did it, but you're making it so hard on yourself.
Yeah.
Okay, we all good? Okay, one of the ways that this is used is on a coordinate plane. Okay, scalar multiplication on a coordinate plane has to do with what we call dilation. Okay, you remember the term dilation where you make a figure bigger or smaller? Okay, so let's say I have this triangle on a coordinate plane. Stop this and start it again.
Wait, so this stuff has to do with